Hello, math humans. We're going to do 1.3b today. We're going to be doing more analytical limits. Our objectives are that we're going to continue evaluating limits analytically. That's a T. The strategies that we're going to use are direct substitution, unless, of course, we get the indeterminate form, your favorite F word factoring, separation, and then multiplying by conjugates. And there are bazillions more, but these are the methods that we're going to look at today. So for our first example, and we're just going to learn as we do, I want to find the limit as x approaches a negative 3 of x squared plus x minus 6 over x plus 3. So the first thing that we should always consider is direct substitution, but if you'll notice, if I put a negative 3 in the denominator, the world might explode, so this is the indeterminate form, okay? So that means that I have to do some algebra. So just like we talked about yesterday, I'm going to carry the notation through while I rework the problem. So this is the limit as x approaches a negative 3, and I'm going to factor my favorite F word, and then x minus 2 over x plus 3. Now those cancel, and again, you have to show all the work. And now I can do my direct substitution. A negative 3 minus 2 is a negative 5. And then I write my conclusion statement at the end as x approaches a negative 3 is a negative 5. So that was a nice, polite way to start our problems. Example number 2 is a little bit more entertaining mathematically. I want to find the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. And again, the first thing we should look at is to see if I can do direct substitution. But alas, I have a 0, which means it is the indeterminate form. So on this one, I'm going to actually do the multiplying by a conjugate, but unlike math that you've done in previous courses, I'm actually going to multiply by the conjugate of the numerator, okay? So I'm going to multiply the problem by square root of x plus 1 over the square root of x plus 1 plus 1, okay? And again, you have to show all of your work. So I'm just going to carry this notation throughout as x approaches 0. Remember, this creates a difference of 2 squares, so I'm going to get x plus 1 times x plus 1 is x plus 1, and a negative 1 and a positive 1 is a negative 1 over x times, I need my parentheses, x plus 1 and then plus 1, okay? The 1's cancel, the x's cancel, which is why we multiplied by the conjugate to eliminate the indeterminate form. Now I can do my direct substitution, and this is 1 over the square root of 0 plus 1 plus 1. 1 plus 1 in the denominator is 2, so this is 1/2. And then I'm going to write my conclusion statement as x approaches 0 of the function was 1/2. So it was actually way easier than it seems. The thing you need to remember is we multiplied by a conjugate to create a difference of 2 squares, which is like x squared minus, let's pick a pretty number, 4. And remember, this was x plus 2 and x minus 2. So I can jump straight from this situation to this situation because the middle terms will always cancel. So that's why when I wrote a square root times a square root is what's underneath the radical, and then a negative 1 times 1 is a negative 1, because it just makes my life simpler. And the algebra is going to get entertaining, so you always want to eliminate as much work as possible. The next thing that we're going to talk about is kind of a cool thing, and it's called the squeeze theorem. And it's a way to talk about a limit by talking about what happens with other functions. So it says if one function is less than or equal to another function, which is less than or equal to yet another function, then the limit of h of x as x approaches c is equal to L, which is equal to the limit of g of x as x approaches c. And remember, as we have defined limits, L has been the limit of the guy in the middle. So f of x is in between, which is why it's called the squeeze theorem. And here's what it would look like graphically. So let's say I had a function, and here's g, and then here's f, and then here's h. So if it were hard to determine the limit of g and h, if f is squeezed in between them, then I could find the limit of the function, because it's going to be what happens to f, which is L. Okay? The last statement that we would write for the squeeze theorem is that the limit of f of x as x approaches c is equal to g of c, the function of g evaluated at c, and the function of h evaluated at c, which was equal to L. So nothing too complicated, but that's kind of entertaining. All right, there are two special limits that you must memorize, because you want to be able to recognize them when you see them, because it's going to make life so much easier. So on our list of formulas that you will be given, you need to memorize this. All right, so for number 1, I have the limit as x approaches 0 of the sine of x over x is equal to 1. And again, this would be something that you just have to memorize. The second one would be the limit as x approaches 0 of 1 minus the cosine of x over x is equal to 0. So on my handy-dandy sheet of formulas, I have written these two things down, and then you would need to memorize those. All right, let's do example 3. And I want to find the limit as x approaches 0 of the tangent of x over x. So if you'll think about this, this is the indeterminate form, because the tangent of 0 is undefined, and so is this. So this is indeed the indeterminate form, which means I need to fix it. And there's lots of different ways you can approach it, but I'm going to manage tangent first. So remember, I have to carry my notation throughout. So I'm going to break this up into the sine of x over the cosine of x, remember that's tangent, times 1 over x. So I just separated this expression from this expression. And now I'm going to rearrange this a little bit. So I'm going to write this as the limit as x approaches 0 of the sine of x over x times 1 over the cosine of x. Okay? Well, we just learned that the limit as x approaches 0 of the sine of x over x is 1. So I'm going to draw my little arrow and show that that piece approaches 1. And then if I do direct substitution, the cosine of 0, remember, is here. Cosine is x, it's 1. So this is also going to go to 1. So the limit is 1. So then I write my conclusion statement, the limit of the function as x approaches 0 is 1. So it's actually significantly easier than it looks. The next example is a cool illustration of, let me pull it back down, this guy right here. And it's just a slight variation. All right, so I want to find the limit as x approaches 0 of the sine of 4x over x. So again, as x is equal to 0, this is the indeterminate form. So that means that I have some work to do to eliminate the indeterminate form. It looks very much like this, but not quite, because of that 4. So I'm going to be a little bit creative, as I do as x approaches 0, and I'm going to introduce a 4 on the top, which means I can also introduce a 4 on the bottom. And this is 1, so I haven't changed the value of the equation, I've just manipulated it a little bit. And this piece, I'll use a different color, this piece is 1. Okay, so it doesn't matter if it is the sine of 4x over 4x, it could be the sine of 100x. But what matters is that the number in the numerator and the number in the denominator match. So then this is 4 times 1, which is 4. So that actually turned out kind of cool. So we made that initial situation happen so then we can do this math. So then I write my conclusion statement, the limit of the function as x approaches 0 is 4. So that really was kind of a unique way to make that happen. All right, I have one more example for us, and then we will be done for today. So this is example 5, and I want to find the limit as x approaches 0 of 3 times 1 minus the cosine of x over x. Well, this one's actually pretty easy because they've done most of the work for you. Remember, this is that special situation, and this guy goes to 0, and 3 times 0 is 0. So that was actually really pretty easy. I could rewrite this, so I'm not going to write my conclusion statement yet. I could have pulled the constant out front and written this like this, 1 minus the cosine of x over x. But I can write this either way. Either way is sufficient. This still goes to 0, and then this is 3 times 0. This is really handy notation to use as our limits become more complicated, to be able to show that a particular portion of the limit goes to 0, because you need to justify your math. This is an acceptable justification. Alrighty, that is it for today. I will see you soon.